In our multimedia example, we've decided to apply what we've learned in dynamics to the real-world system of an independent front suspension, or IFS, and we'll get started by introducing exactly what that is. So here we're going to be looking at an independent front suspension. In these two images, you can see that each of the wheels in the front end have independent front suspensions. This allows each side of the system to freely react to forces acting on each wheel, independent of what's happening to the wheel on the other side. This has a few advantages that we will cover once we've done some calculations. So one of the many other kinds of suspensions is a solid axle suspension. A solid axle suspension has a rod connecting the two wheels, which makes the two wheels' positions always relative to one another, which has its own advantages and disadvantages in practical applications. Solid axle cars are generally better for rock crawling and off-roading, and are more efficient for applications that don't necessarily require independent suspensions. So you might be asking, okay, an IFS is a thing, but what is it used for? And are there different kinds? The answer to that is yes, and it's going to be your job to analyze two common linkages. So on the left, you can see a 5th generation freeboard, and on the right is an IFS of an off-road buggy. So here we have a simplified look at those two systems, and this is what we'll be looking at for our analysis.
Starting with the freeboard suspension. Notice as I trace the axle's endpoint, it forms an arc. Now notice as I mark the axle's orientation that it is always radial from the center of rotation. Next, we look at the parallel bar system. Notice how the axle follows the same arc as before. But now, when marking the axle orientation, it is always horizontal. Here's a little bit more info on these systems. In the picture on the left is our linkage 1, or the freeboard skateboard suspension design. In this design, the wheel always rotates perpendicular to the actual bar that it's mounted on. When the spring is uncompressed, the bar is at an angle below the horizontal. In our picture on the right is linkage 2, or an independent front suspension system like those found in most modern cars. The wheel remains mostly perpendicular to the road when the suspension is both loaded and unloaded. When the shock absorber is uncompressed, the parallel bars are at some angle below the horizontal. Now, how will each suspension system move when a force is applied? In our freeboard system, the wheel follows an arc path and also rotates with the control arm, as does the force. The singular control arm provides all the structural support the design needs. In the independent front suspension, it also follows an arc path, but the orientation of the force remains in the vertical direction. Dual control arms allow for more structural considerations, though, in our calculations.
Okay, let's solve. But wait, we have to make some assumptions first.
These are assumptions that we've made so that the concept is much easier to interpret. The spring's mass and friction are unnecessary as we are only observing the motion of the arms. Both systems must have the same dimensions so the differences in motion are clearer. The masses of the arms are also the same, so energy expended is the same as well. The spring constant and unstretched length must also be the same to analyze the motion and velocities. Here, we have the calculations for the arc distance the wheel traveled when the spring goes from an unstretched length of 13 centimeters to a compressed length of 9 centimeters. We used the law of cosines to find the value of theta when the spring is unstretched, and likewise when stretched. Then we found the arc length by taking the radius of the arm and multiplying it by the difference in theta. And here, we use work and energy equations to find the force needed to compress the spring fully. since the force from the ground is non-conservative. Now that we were successful in finding arc length, delta theta, and ground forces, we can apply what we learned to solve the unknowns for the car suspension.
To start this problem, we're going to draw our energy diagrams with the uncompressed linkage and the compressed linkage. We'll also need to find our dimensions, our angles, our heights, so that we can plug those into our energy equation. The only real difference between this second linkage from the first is that the direction of the force applied always remains vertical. It doesn't travel along an arc remaining perpendicular to the control arm. It actually always remains vertical because of the orientation of the wheel for this linkage. For that reason, the distance traveled for the work done term in the energy equation, it only includes the vertical distance that force traveled. It doesn't account for that horizontal distance. So the vertical distance that the force traveled is going to be delta y, or 2 times the height that the center of gravity of the control arm is moving. So we just plug in that delta y, which equals 2 delta h, and we have the distance traveled for the force. After solving, we find that the force actually equals 14 newtons, which is larger than previously with 13.654 newtons. So what does this tell us? Basically, it takes more force to load the car's independent front suspension than the freeboard truck suspension. Even though our models are on the same scale, they use the same spring, and all of the control arm's masses are actually identical. This is simply based on the linkage and the way that the force travels and moves as the linkage moves. This has nothing to do with size or mass. However, with increased size and mass, this difference between the two would be much greater. Essentially, this means that the car's IFS could be better for handling larger loads without bottoming out that suspension. And that's why we see cars use a design similar to this as opposed to with the wheel rotating. This also has other advantages, of course, and we'll go over some of those now. As you can tell by now, these suspensions have been engineered for different purposes. On the left, we have the freeboard linkage. As the rider leans and tilts the deck, the wheels always remain perpendicular to the level ground. This allows for maximum friction between the wheels and the ground, which, as the rider goes down the hill, they need that maximum friction to remain in control as they're constantly making slides and turns. On the right, we have the car IFS. This suspension with 2 control arms is designed so that the body remains somewhat level as the vehicle continues on its travel. This means that hitting bumps in the road doesn't pose a huge disturbance to the passengers in the cab. While we were able to cover 2 different kinds of simplified linkages that are used in engineering and transportation applications, we weren't able to cover all the kinds of suspension that are out there. So please feel free to reach out if you have any questions regarding this material, our solution process, or its application in the real world. Thank you for your attention, and feel free to contact our group via the email that is listed below.